computer. There we go. All right. Desktop, share, there we go. Okay. So I can see that. There we go. All right, so sorry, cell phone is making noises. Welcome everyone again. I'm really glad to have you here. And again, hopefully we will all be in ECCR 130 something or other in 2 weeks. So speaking of which, what I'm going to do, unfortunately, is the same thing that everybody else has done to you yesterday and today, which is to go over the syllabus a little bit. So my syllabus is on my webpage, and this is actually something that's important. I have a separate webpage for this course. I do use the Canvas webpage for this course, but I also have a separate webpage for this course because I want people to be able to access it who are not registered for the course. So it looks clunky, deal with it. I'm sorry. I'm not very good at webpage design. I do post things like, passcodes for Zoom lectures on the Canvas page, because that way, excuse me, I'm going to pin myself. There we go. We got Zoom bombed last year, so I keep those private. So here is the web page for the course. You have the link for that. I warn you, I have a cat and he'll get involved in this. My apologies in advance. So most of the syllabus is totally self-evident and you can all read, so I'm not going to read it to you. You know where we're meeting. Well, actually, here's where we're meeting, ECCR 151. This is the web page. This is me. You're welcome to call me Liz. You can find me on the 7th floor once we're allowed back in there. I have some office hours. I'm going to have Zoom on during those office hours. So if you have a quick question, you just want to drop in on Zoom, please feel free to do that. I do have a couple of conflicts with those office hours, so check my web page before you stop by in case something's come up. We have a wonderful course assistant named Ella. She took the course last semester. She's going to have help hours on Mondays. This might be something useful to you because the problem sets are due on Tuesdays, so you might want to note that down. We're going to get some physical locations for that. I don't know yet where they are. There's a whole bunch of boilerplate about the course. This is new. Because we are remote only, I checked the box to offer you guys digital access to the 2 textbooks. And as I emailed you the other day, this is an opt-out thing. You'll see a bill on your tuition bill for $110 unless you opt out. So if you've bought them or you want to buy them, remember to opt out. You need to do that by the 26th. I'll try and send a reminder. So that makes things easy for now. And the bookstore has assured me that that's actually cheap. My goodness, textbooks are expensive. We will be using some other online materials. I teach a course, a version of this course through the Complexity Explorer MOOC, Massive Open Online Course Platform through the Santa Fe Institute. It's a highly watered down version of this course, but the videos might be useful to you. So I have incorporated them into this class. They're short videos. There's a couple to watch that are associated with each of my lectures. They're optional. You don't have to watch them. They're useful if maybe you miss a lecture or if a concept is muddy or something like that. There are unit tests on this MOOC that are part of your grade. So you need to do those. You can do them in line or you can wait until the end of the semester. Past students have found that this is actually a good way to study for the final. So this is for you to use as you see fit at whatever time of the semester you want, before the lectures, after lectures, whatever, or not. Just you do have to take the unit tests. And speaking of making up for things and missing lectures, an awful lot of this course is not in any textbook. It's just in my big fat notebook that I've been amassing for 25 years about this. This is my research area. So a lot of the course is also just in my head. And given that we're not going to be recording lectures other than this first couple, you really do need to come, or else it's going to be very hard to get hold of the material. This is an elective. It's one of the harder courses in the curriculum. I know that. The people who register for this course are motivated. I don't bother you with lots of midterms and things like that. There are a bunch of problem sets, and then there's a final, and that's really it. If you're a grad student, you'll do a project for the last 3 weeks, and we'll talk more about that later. The final is pretty qualitative, and again, that we'll talk about later. They just posted the final schedule. Our final is on Tuesday night of finals week. If you have 3 finals that day, please look and get in touch with me so we can figure out a workaround so that we can do something else, because 3 finals in a day, you're not going to have a brain by 4:30. Blah, blah, blah. I said all that. Again, this is a very mathematical course. I think it's really cool stuff, in case that's not obvious, and I hope you will too, but it's not something you can kind of coast through and not work on. And it is important not just to come to lecture, it's important to do the problem sets because they build on each other. And if you don't do, for example, problem set 4, you're kind of hosed for the rest of the semester. So please keep up with them. Collaboration. Collaboration is a great way to learn stuff, but it's also a great way to avoid learning stuff. And I want you to do the one and not the other. Please feel free to work together at any stage, but what you turn in this course has to come from your head through your fingers without, kind of copying or doing anything else that will avoid you learning the material. That's what I care about. And that's our policy. There's a lot of code on the web to do this kind of stuff. I don't want you to use it. And there's a couple of reasons for that. This course is a computer science version of a course that's often taught in applied mathematics. And the reason for that is that the computer is the laboratory tool for this field. And it's very easy to have your tool run amok on you and not know. So the difference between applied math version of this course and my course is we really dig into the computational aspects, how the tools work that we use as a laboratory tool, and what the implications of that are. So that's why one reason why I want you to actually write all this code. The other reason is, in my experience at least, when you download code from the web, you just stop thinking. You don't think, you just say, oh, I downloaded it, I'm just going to use it. And that is not going to work in this course. Everyone at this point, I'm sure, is computer literate. This is the rant about canned software that I just delivered. I'm not going to look at your code. You don't need to turn it in. I'm interested in what comes out of it. And you're thinking about that. And in fact, in this course, if you get something's not working and you turn in the picture and you say, this isn't what it should look, should look like that, you'll get most of the credit. So I'm interested in the thinking in this course as much as, maybe even more than, the results. There's a grading formula which you can read. Class participation will bump your grade up in this class. And that doesn't mean just coming, it means actually participating, saying something. There's a syllabus. CU syllabi have gotten very long because they keep sending us more and more stuff to put on them. So you've probably seen most of this. I will highlight the parts that are different and synopsize everything else. We all need to be good about COVID, especially with Omicron. It's not as bad, but it's much more infectious. Blah, blah, blah. If you feel sick, please do not drag yourself in and to class. It's not worth it. We can work around this. So do not come in sick. Email me if you trash your shoulder skiing. Email me. We can work around it. This class ends up being a smaller group and a kind of a community, and we can get people to take notes for each other. And that's a learning experience for everybody. So email me and we'll figure it out. This is behave nicely. This is if you have a disability. There are ways around that. This is what I just said about trashing your knee skiing. If you have a different name or pronoun that you wish me to use, please let me know. Happy to. I'm terrible with names, so I will probably forget no matter what, but I will try. Religious obligations, obviously, if you need to go, well, I guess the high holidays are over, so don't worry about that, but let me know. Don't be nasty about sexual misconduct. Oh, this is important. I'm happy to be a sounding board for you around issues, even if they're not around the class, but I have an obligation to report. There's a certain set of things, there's a boundary. And if you tell me something that's over that boundary, I can't keep it quiet. I have to take it up. So let's be careful with that. Honor code. In this course, I told you what the honor code is. I don't care how the material gets into your head. What I care is that it's in there and it comes out from you to me. This is not CU boilerplate, and it's actually important, especially in mathematics. The sources, the primary sources, are not very many women, not very many people of color. There are some hidden figures in this field. Remember that movie? And we'll talk about that over the course of the semester. But all the theorems have guys' names on them. It's just the way it is, and I will try to work around that as much as I can. And this is, again, this class does turn into a bit of a community, and I really like that about it. Any questions on that? Feel free to just sing out. I have a little tiny window for Zoom, so you're going to have to say something to get my attention rather than raise hands. Okay, so here is the chaotic system. Hopefully this will, there we go. It's a double pendulum. It's 2 pieces of aluminum and 4 ball bearings, okay? And put it on a hard surface so it doesn't damp. And this is what it does. This is a classic chaotic system. Very, very simple physics, mg sine theta and so on and so forth, but it does incredibly complicated things. But if you know how to look, there are some patterns in this very complicated behavior. And that tandem of structure and complexity is what I think is really cool about the field. And that's what we're going to dig into. Before we dig into that, let me get back to PowerPoint. Oh, by the way, I'll try to do this, listing which videos are associated with this lecture. And each unit on the MOOC also has these quizzes. Those are not graded, so you can take those as much as you want. They can be a good diagnostic for your understanding. Okay, so background. What do you need to know in order to get through this course? You need to know basic physics, things like pulleys and F equals ma and torque and things like that, the first semester of physics. You need to be fairly comfortable with derivatives, not so much integrals, but certainly the first semester of calculus. If you've had an ordinary differential equations course, things will be easier, but I will go through what we need from an ODEs course, and there are some notes on the webpage that will help you. This is a course about nonlinear dynamics. Nonetheless, linear algebra can actually be useful because you can approximate a nonlinear system as a linear system, and that can give you some traction. And I think everyone in here has had that. If you've had 3656 or another numerical methods course, that will help because you've seen ODE solvers. And obviously, you need to be able to program. Okay. So the kinds of, wish my Zoom window were not on top of that. The kind of mathematics we'll do, and I'm going to see if I can't switch to my document camera and actually get things in. There we go. So mathematics, this should not terrify you. So the notion that we have some function x of t, okay, and we don't know what it is, but we do know something about its derivative. So we're playing Sherlock Holmes. We have this thing, it's a function of time. By the way, dynamics, the word dynamics means to change, to evolve. So all of the derivatives in this course are going to be ddt. And we're always interested in how things change with time. So there's some function x of t. We don't know what it is.
We can't see whatever you're writing down. He still has the slides up on Zoom.
That's bizarre. Thank you for letting me know. I thought
I can see it. You should just swap shared screen with video.
I shared the whole desktop. That should work. Is that working now?
We can see it in the video. I mean, whatever you're writing on paper, we can see.
You can see it.
If you pin her video, you'll be able to see it.
Aha.
Yes, exactly.
Gotcha. Okay.
Okay. Thank you. All right. So some function, we have to play Sherlock Holmes. We don't know what this is. We want to know what this is. But what we do know is that its first derivative with respect to time is 1. Okay. So functions that look like that are, well, actually, I need another bit. So I also need to know that at t equals 0 at some fixed time, maybe the thing is also 1. This is called an ordinary differential equation. This is called an initial condition. So at t equals 0, x is 1. And after that, well, we know from this equation here that the slope is 1, right? That slope is 1. Now, this thing has lots of other solutions, right? It has this one and this one and this one and this one and that one and that one and so on and so forth. So this thing here has an infinite number of solutions, all of which have a slope of 1 in the time domain. This thing here is a thumbtack that says it's this one here. That's our solution. All right, so let's crank it up a notch. So this, by the way, this is called a solution to that ordinary differential equation from that initial condition. All right, let's say instead that I knew that ddt of x of t, and I'll use shorthand for that. I might use x dot, I might use x prime. Sometimes these are shorthands for that. And it's equal to x of t. So the function is not, the derivative of the function is not 1. The derivative of the function is itself. So we need to think about what functions are their own first derivative with respect to time. And those are things that look like e to the t, right? Because if you take ddt of e to the t, you get e to the t. It's also true if it's k e to the t, because if you take the derivative with respect to the time of that, you get it back. It's not true for that, because if you take the derivative of that, you get k1, k2, e to the k1t. So that's not a solution, but this is. So all exponentials are solutions to that differential equation. And let's say we know again that x at t equals 0 is 1. It says it's that one. It's not this one. It's not that one. It's not this one. It is this one. That's the solution. So hopefully this kind of stuff, most of you are bored. Some of you are remembering your calculus class that may have been a long time ago. If any of this is worrisome, you can look at my ODE notes. If it's absolutely terrifying, email me and we'll talk. But let's try one more. X double dot is equal to minus x. Now you notice I've lost my t because in this course, every function is a function of time and every derivative is a derivative with respect to time. So here's the ODE. And let's say the same boring initial condition, x at time 0 is 1. That's a 1. Now, this is more interesting. What kinds of functions are their own negative of their own second derivative? Well, those are things like sines and cosines. So actually, technically, it would be sine of, well, we'll just say sines and cosines. That's enough. Because if you take a sine and you take its derivative, you get a cosine. Then you take its derivative, you get a negative sine, right? Yes. So sines and cosines are the solution, the possible solutions to that ODE. This pins it down. So that says that the solution has to be here. So that says that this is a cosine, not a sine. So cosine of t. Okay. Now, let's see if we can switch off of. There we go. Okay. There are much more codified ways to solve ODEs. Those are the topics of an ODE course. We will not go that route because any ODE that is interesting from the standpoint of this course because it is chaotic, by definition, cannot be solved with paper and pencil. And not just that it cannot be solved, there exists no solution. There exists no solution that you can write down and eventually stop writing. It's what's called non-integrable. Non-integrable. Go back to PowerPoint and go forward. There we go. For those of you who have a bit more math background, that's why the quotes are here. I'm abusing this term a little bit, and I'll come back to that. So because of this, we're interested in the kinds of systems that you can't solve in closed form. We will take the practice of looking at the differential equations and saying, oh, aren't those nice? And then we will drop them straight in an ODE solver that does the solving work for us. Now, an ODE solver does not produce a closed form solution. In this case, it can. What it does is, if you give it a state of the system, it tells you where the system is a tenth of a second later, and a tenth of a second later, and a tenth of a second later. That's going to be our solution. Now notice it's not the full solution. It doesn't tell you for all time. It just gives you some samples, and we'll come back to that. So that's this notion of non-integrability, by the way, that is a necessary and sufficient condition for chaos. This is a necessary and sufficient condition for chaos. Remember this thing? This is a necessary and sufficient condition for chaos. That says if this true, that true, and that true is that true. So it goes both ways. It's not one of these, and it's not one of these. It's actually one of these big, powerful ones that look like that. This is a necessary condition. There is a necessary condition for chaos if you're do it this way. Chaos, you have to be nonlinear to be chaotic. So if this is a necessary condition. Hopefully I've got the arrow back the right way. So it is certainly the case if you're chaotic that you have to be nonlinear, but there are nonlinear systems that are not chaotic. So you might want to remind yourself a little bit of this business of necessary and sufficient conditions, because those will come up. Okay. So the kind of physics we'll do is, again, that first semester physicsy kind of stuff with things like pendulums. So here's a pendulum. It's a mass of mass m hanging on the end of a rigid massless rod of length L. And you can describe where it is using some angle theta. It is being pulled upon by gravity. We know how that works. But because it's on this rigid massless rod, it can't go that way. And what happens is that the device does a projection of this force in the tangential direction, and the size of this is mg sine theta. And the only hard part here is remembering whether this is a sine or cosine. I always have to rederive it in my head. Think about if theta is 0, the bob is here, the gravity is here, then there's none of the force that's going crosswise. That tells you it's a sine. Okay, so how do we deal with this? Well, there's this very useful equation that I hope we all remember, F equals ma. This thing is a mass m thing, and it's reacting to this force right here. It also might be reacting to some friction, because everything has friction in its face. So this is the gravitational force projected, and this is the friction force that's opposite of its velocity. I shouldn't actually draw that arrow because I don't know which way it's going, but anyway. All right. With pendula, it's much easier to work with polar coordinates than it is to work with Cartesian coordinates, because the natural physics kind of lives in a polar coordinate space. But that thing right there is in Cartesian coordinates. Really what we want it in is polar coordinates. So instead of x and y and x dot and y dot, what we want to work with is theta. We want to work with omega, which is d theta. I'll just do the dots. It's theta dot. And alpha, which is theta double dot. This is in radians. This is in radians per second. This is in radians per second squared. Position, velocity, and acceleration in polar coordinates. So we need to rewrite this thing. So that means we need to be able to convert between alpha and a. And to do that, you just think about driving your car around an exit ramp to a highway. If you are going 90 degrees of the way around that ramp, how fast you go depends on the radius of the ramp. If it's a great big radius ramp and you go 90 degrees around it, the arc length is very long, so you've had to go fast. If the radius of the arc is very small, you've only had to go this far in the same amount of time. So it depends on L. And the way to convert this is to think about A in terms of alpha, and the conversion factor is just an L. So we're going to need that when we write F equals ma in this frame. And looking at this, one derivative, two derivatives, that says that this is equal to L theta double dot. Now, in the real world, there's friction. In your beginning physics classes, they probably left that out and then they sprung that on you a little bit later. Friction comes in many, many forms. The very most common one is proportional to the velocity of the thing that's moving. There are lots, there's real life friction is very, very different, but let's just treat with this. So here is a proportional, this is the friction coefficient times the velocity. But again, we need to convert this to omega somehow. It's the same thing. It's beta times L times omega. So there's the friction term. This is going to help us with MA. And here's the force. So we basically have everything we need right in front of us to write down F equals MA, or to write down a force balance, which says F minus MA equals 0. So here we go. I'm just taking this and multiplying it by M. I'm writing my theta badly. And I'm putting them all on one side. Now, this thing right here is that little orange force. This thing right here is that little frictional force, like that. The reason that these are different signs is because friction always points against your velocity. The only remaining brain twist here, because we've gone through all the terms, is the signs. So spend a little bit of time thinking about that. And if you're worried about this sign here, think about, well, if I'm here and this is pulling that way, this is making theta smaller, and so that creates the acceleration. So I'm going to leave that for you to think about a little bit. This thing here is a second order ODE. This is the kind of thing that we need to solve in order to figure out theta of t, which is our desired solution. Why is it a second order ODE? It's a second order ODE because the number of dots and kind of the thing with the most dots is 2. So it's a second order ordinary differential equation. And we're going to see lots and lots and lots of those. Actually, not so many, because second order ODEs cannot be chaotic. You have to be three-dimensional to be chaotic, and I'll come back to that. But first, let's think about how to get something like this into the format that ODE solvers like to ingest. ODE solvers would kind of hiccup on that. They want ODEs in a slightly different format. They don't want it in the form of an nth order ODE. They want it pulled apart into a system of first order ODEs. And I'm going to show you how to do that. First of all, let me write the equation on this slide so I can go back and forth. Let's do a simpler version. Let's take, hello, my pen just stopped. Without the friction. So let's just take ML theta double dot plus mg sine theta equals 0. That's a second order ODE. And oops, lost my theta. And we're going to convert it into a set of first order ODEs. This procedure, doing this, is covered in my ODE notes, which are on my webpage. So you can sit back and just watch and not have to write stuff down and go back and consult those. The first step is to get that highest order derivative by itself on the left-hand side. So basically solving for this thing. Watch me on math. I have especially when I get excited, I lose minus signs all over the place. So first solve for that highest order thing. Then you define some helper variables. In this case, because we have a second order ODE, we only need one helper variable. And I'll show you what I'm going to define. And I'll explain it in a bit when we get the full system done. And then the third step is basically just to rewrite. And you get your system. You get, let's see, theta dot equals omega, and omega dot equals, and let's cross off these m's, minus g over L sine theta. Okay. This is a set of two differential equations that is exactly the same as this thing, except where this thing is kind of short and fat, this thing is kind of tall and thin. And again, the advantage of this, well, there are lots of advantages of this. First of all, if you're going to use an ODE solver, this is how it has to have its input structured. But this also brings out lots of other important points. If you think about a pendulum, so that I don't, well, all right, I'll switch cameras. There we go. Here's a pendulum, okay? This way. There we go, pendulum. If you want to describe the state of a pendulum, you need to know two things. You need to know where it is, and you need to know how fast it's going and in what direction. So you need to know theta, and you need to know omega. Omega is the angular velocity. Those two numbers completely describe the state, air quotes, state of the system. Now, state is a loaded word. Okay, let me go back to this. So the state of a system, loaded and circularly defined. The state of the system is the numbers that you need to describe the state of the system. There are better ones, but we all know what we mean. And this is a difference between this course and the applied math version of this course. Is I will wave my hands wildly about things like this as opposed to defining them, because I want to get to applications. Okay, so the state of the pendulum, you need to know two numbers, theta and omega. It's not obvious why you don't also need to know alpha, but you don't, and we can talk about that offline. So this set of equations, if you look at the equation in this ODE system, it kind of exposes the fact that these two things are the state variables. And you can stack them up in so these are the state variables. And you can stack them up in a state vector. And you can think about the space whose axes are these state variables, which is the state space. And you quickly, if you think about it, you can see that this thing here, this whole thing, is a box of mathematics that takes a theta and omega and spits out theta dot and omega dot. Okay, that's what that is. It's a box of mathematics that says, given a state of the system, how is that going to change? And again, dynamics. This is the course about dynamics and change. So this is the basic system of physics that tells you, given a state, it doesn't tell you where you're going to be next. And that's an important distinction. It tells you which way you're going. So you can also think about this as, given a state, which is a point in this state space, what this box of mathematics does is it tells me things are going to go that away from that point. And you've probably seen these definitions of an ODE, if you've taken the course, defining a vector field on the state space. You can think about this, that should be like this. If you have a bunch of leaves and you kind of roil your rake in a circle and you can see how things are going, this is what an ODE defines, is it tells you for every state of the system, for every point in the state space, what's the derivative? If you're a skier, this is pretty easy. You think about, a hill, and for every point in the hill, the derivative is the way your skis are pointing. It's the fall line. So what's the fall line at every point in this two-dimensional space is defined by this ODE system. Okay, so we also talk about the dimension of the system, which is the number of equations in the first order ODE system. It is the number of dots in that thing. It is the number of state variables. It's the length of the state vector. We always do columns. I don't know why. It is the dimension of the state space. Okay, so this representation of the state space is incredibly powerful. It will be the space that we work in probably 90% of the time this semester. It does suppress time a little bit, and we'll talk about that. But what it does in suppressing time is bring out patterns, which is what we want. Okay, so the pendulum, my pendulum, cannot be chaotic. Okay, pendulum cannot be chaotic. Another necessary condition for chaos is at least 3 dimensions. Okay, So your state space has to have 3 axes for chaos to arise. And the pendulum just has 2. So we know that the pendulum can't be chaotic because of this. So this is, by the way, this is just true in continuous time systems and discrete time systems. As we'll see, that's not the case. Okay, so in classical mechanics, if any of you have taken that, we think about degrees of freedom in the system. So like my elbow has hopefully just 1 degree of freedom. There's just 1 angle along which it bends. And so to completely describe the state of this system, I would need an angle and an angular velocity for that degree of freedom. My wrist has this angle and it has this angle. Okay, so 2 degrees of freedom. To completely describe the state of this system, I would need 2 positions and 2 velocities. So it would have a 4-dimensional state space. This would have a 2-dimensional state space. This would have a 4-dimensional state space. Shoulders, excuse me, 1 degree of freedom, 2 degrees of freedom, 3 degrees of freedom. So I need 3 numbers to describe the state of a shoulder. And, or sorry, 3 degrees of freedom, I need 6 numbers to describe that state, 3 positions and 3 velocities. This is why motion capture data gets very, very big, because motion capture makes a 3D model of a human body, especially for like the motion capture that was used in the movie Avatar. Those vectors had to have been, you know, the state of that system is hundreds and hundreds of variables for each snapshot of a critter. Okay, so my double pendulum that I showed you before has 2 degrees of freedom. It can do this. If you can actually, let me do it up here. It can do this. That's 1 degree of freedom. And it can do this. That's another degree of freedom. So overall, it has 2 degrees of freedom. So I need 4 numbers, theta 1, theta 2, omega 1, and omega 2 to describe its state. So it has 4 dimensions. So the double pendulum has, it's a 4D system, theta 1, theta 1, omega 1, theta 2, omega 2. That would be the state vector. The state space is 4-dimensional, which is hard to draw. And note, that means that the double pendulum can be chaotic, even though the single pendulum cannot. So, PowerPoint. There we go. So here are some words that go along with the movement of that pendulum. And I'll get it to, there we go. So this system is a simple system. It has, hope you can still, I'll yell so you can hear me. It's very simple. It's 2 blocks of aluminum and 4 ball bearings. It's not trivial, but one can write down the differential equations for this. And even though those equations are deterministic, the behavior is incredibly complex. It's not random, by the way. It's not random at all. And if I started this thing at 2 very similar initial conditions, just like this and like this, it would do different things. Okay, even though the initial conditions, by the way, are values for theta 1, theta 2, omega 1, and omega 2. Here's one, here's another. This is one set of 4 numbers. This is another. So looking at the PowerPoint slide, you see a lot of words. Let's go through some of them. All right, complex behavior arising in deterministic nonlinear dynamics. Okay, nonlinear. What does nonlinear mean? That means that somewhere in the differential equations, there is either a product, a power, or a transcendental, or lots of them. At least one. Any one of those things will infect the entire ODE system with nonlinearity, because you notice that they're coupled. The equations are coupled. One variable affects the other, and this variable affects that. So nonlinearity, functions that are not A times variable, constant times variable plus constant. Anything that is not one of those is a nonlinear system. The world is basically nonlinear, so we need to deal with this. Dynamic, I told you what this meant. This means it comes from the Greek dunamos, to move, to evolve. Dynamic systems, things that move or evolve with time. Many people put an AL there, dynamical systems. I alternate, doesn't really matter. Deterministic, this is important. If I take this thing and I drop it, it's going to fall. There's not a large chance that it's going to go down and a small chance that it's going to go up. The current state determines the future state. There's no random variables in these equations. But because of that extreme sensitivity, these systems can be effectively unpredictable. And the way to think about that is, if we have something like this, it's incredibly sensitive, that if I release it here or here, it does something very different. Well, you know, there's air molecules running around in this room. If an air molecule bonks this thing, that could change the future course of its behavior. But if I'm not thinking about air molecules, that looks like randomness to me. So effectively unpredictable, even though they are deterministic. And that's another kind of mind twist that makes people like me get interested in this field. All right, so that's the setup here. And chaotic systems have two special properties. They have that sensitive dependence on initial conditions, which is that extreme sensitivity, but they do have characteristic structure. And if you have the right set of glasses, if you know how to look, you can see those patterns, and we'll spend a lot of time doing that this semester. And the words at the bottom of the slide, this is not an ivory tower academic thing. This happens all over the world, all over the universe. It is ubiquitous. Okay, that's what that means. And you don't have to be complicated to be chaotic. So it's not just fun, it's actually really useful. Another example that we often use in my field is an eddy in a creek. So go down to Boulder Creek and there's a rock under the surface, the water is flowing over the rock. And because of that, there's this swirly patch of water that forms on top of the rock. If you stood there and watched it, it would look kind of the same. The structure of the eddy would be the same. It's always this big. It's always kind of this part's flowing that way and this part's flowing that way. But if you took a wood chip and you dropped it in that eddy at one place and watched, did a time lapse, the wood chip would go around the eddy and then go out. Move that wood chip 1 angstrom to the left side, and it might go 3 times and then out that way. So sensitive dependence on initial conditions. You've also probably heard of the butterfly effect. Okay, the butterfly effect. I wanted to show you this video. This is a great video it's a GitHub animation of what happens of basically the hand waving that I was doing. If I start this pendulum here, 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 what happens? So this guy has made this beautiful animation of this. Flip to Safari, and I think it's here. Where is it? Oh, it's down by, I did this for a reason. So my webpage has all of the assignments, by the way. All the assignments are on here. This problem set is nominally out today, and it's due next Tuesday. So I will not put these on Canvas. I will try to remind you about every single one of them, but this is where you get them. I normally pass these out on paper so we all remember, and also so that people have something to scribble on as I'm talking about the problem set during class. But for now, obviously, we're not doing paper. And as you see, like under problem set 5, here's a bunch of useful stuff. I also have a whole bunch of, this is a total rat hole. There's too much fun, interesting stuff to look at. Here are all my written materials and videos. And down here someplace, here we go. There we go. So let me stop this and rewind it. Again, what's going on here is this person has written an ODE solver, fed into it the equations for the double pendulum, and tried a whole bunch of different initial conditions and let them go. You can see why I called it trippy. So this is sensitive dependence on initial conditions in action. Stop this, go back to PowerPoint. There we go. And there's the link if you want to play with that, you can get it from my webpage. Okay, and then there is the butterfly effect, which people I'm sure have heard about. It's a useful metaphor, probably not very useful in practice, but a butterfly flapping its wings could set off a hurricane across the world somewhat later. This, begs the question, well, what if we wanted to steer the hurricane? We could try to figure out where to put the butterflies to steer the hurricane. In theory, sure. In practice, never, because you would need to remember that business about incredible sensitivity. You would need to have perfect knowledge about so many things in order to get this to work, let alone the ethical challenge of what about the people that it hits now that it was going to hit and you steered it someplace else. So we don't go there. I have done some work on this in a laboratory, and I'll talk to you about some of that later. Now, why is this a computer science class? Goes back to that business of the computer is the lab tool. A dynamical system in the form of an ordinary differential equation, by definition, cannot be solved in closed form. It's not just that you can't solve it or I can't solve it, it's that the solutions do not exist. That is, there is no finite amount of writing you can do to write down the form of the solution and ever stop, and no cheating with infinite sums or series or things like that. So that defines the systems are, don't have an analytic solution, they're non-integrable. So you have to solve them with some sort of ODE solver, and you'll become familiar with these words in a few weeks. You might already from a different class. So if computers are necessary to solve these things, it's pretty obvious that this couldn't really be done. Well, I mean, sure, you could have a room full of people doing the calculations under fourth order Runge-Kutta, and they did do that in World War II, and we'll come back to that. Before this could be automated, this was a major pain, and so my field only really took off about 40 years ago. Okay, let's go back to the pendulum differential equations. Switch. All right. Oh dear. I bought a really cheap document camera. Actually, how about this? Can somebody screenshot this and Google to see if this has a focus block, please? And sing out if you find it. Stupid thing. Anyway, my apologies. I had a nice one from the dean's office, but I didn't have time to get one. Anyway, so back to the pendulum differential equations, which look like this: theta dot equals omega. And let's take the simple versions of this. It's minus G over L sine theta. This is a two-dimensional system. Okay, so a 2D system. There are two equal signs in the system. There are two state variables. Those are all synonyms. So it cannot be chaotic. Okay. It is nonlinear because over here on the right-hand side, there is something that's not, that is a power, a product, or transcendental. Here it's a transcendental. Okay, so they're nonlinear. Okay, where am I going? Oops. But I don't know if you remember that trick. When theta is small, sine theta is approximately equal to theta. Remember that trick? Look what that does to these equations. Okay, it changes this sign into just a theta. So it changes the equations to look like this. These are constants, and here's a variable. If you substitute these in together, you'll actually see that this looks like, so I'm telescoping these together, I get theta double dot equals minus G over L times theta, which looks suspiciously like the example I did at the beginning of the class, right? Because it's something that is the negative plus a constant of its own first derivative, of its second derivative. This happens to be the equation for a mass on a spring. This is called the simple, LE, harmonic oscillator, or SHO, simple harmonic oscillator, has these equations. G over L might be different. There's going to be some K and some M, and it's, it's a Hooke's law spring, so it pulls back in proportional to how much you yank on it. So it wouldn't be G over L, it would be K over M, but modulo a constant. This is the equation for a spring mass system. These can be solved in closed form. Okay, so we did that, right? We did solve that in closed form. So we can solve the simple harmonic oscillator equations in closed form, and we get sines and cosines, if you remember that. So sine or cosine, depending on the initial condition. And you also can imagine plotting the behavior for the spring mass system. Draw it again. If we measure X from the equilibrium position of the spring, lumpy mass, there we go. The state variables of the system are the position and the velocity, and here's the state vector. And so we actually need to plot two things. If we were working in the time domain, where this would be some sort of sine, maybe. I got to get this right. This is not completely trivial to draw. So here it would be, this is maximum positive, so that's 0. This is 0. This is 0. Here, this is going in the positive direction, so there we go. That's what the position and velocity look like for this mass. You pull it down, and it's going to go wooga, 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 and there it is. In the state space, first of all, the state space has the axes X and V. This initial condition is at X equals 0, V equals something. Oops, sorry, wrong. There's the initial condition, that's wrong. And what these two combine to look like on the state space, this is what you see. Let's see, do this right. If you're looking at this thing, here's my eye. If you're looking at this thing from here, you see that. If you're looking at this thing from here, you see that. So overall, what you see is something like that. And it's going that away, if you think about that. So here's time domain and state space portrait of a solution to the simple harmonic oscillator ordinary differential equations. If there's friction in the system, then the time domain plots die out. I've not drawn this right. I've drawn it with a decreasing period. I shouldn't. Give me that. Oops, cat is here. Hang on. There we go. And in the state space, what you'll see, same initial condition, like that. And that is what this device, now the cat is in the back of the chair. He likes to do this. My apologies. This is Tristan. Where's Tristan? There's Tristan. Get down, 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 down. This is one of the disadvantages of teaching from home. Blah, blah, blah. Where was I? Hopefully he didn't disconnect us. Okay, so here is this pendulum. And here I've started it, and it's swinging down, and it's slowly swinging down. Let me actually help it. There we go. Swinging down, and it's eventually going to end up stopped, just like my drawing. My drawing is converging to a fixed point at the origin of the state space. That is, it's converging to a point at X equals 0 and V equals 0. Now I'm scratching the chair. Excuse me, I need to close the door. All right, so this is converging to a stable fixed point. It's stable, by the way, because if I bonk the pendulum, do it this way. If I bonk the pendulum, it's at this fixed point, and I bonk it. Ooh, that's really sticky. If I bonk it, it'll come back. So it's a stable fixed point. We'll go through that vocabulary later. Okay. We did all that. Yes, okay. Now, all of this was for the approximation here. When this approximation holds, is only valid when theta is equal to small, and theta is small. Sorry, speak English. So you can solve the pendulum equations for just that little bit of right here. If you have the pendulum living just in the small theta space, these equations hold, and we know how to solve those, even if there's friction. But if theta is not small, and this is, I'm switching to the PowerPoint here. If theta is not small, obviously if theta is not small, the approximation isn't valid, so those solutions don't apply. There are ways to solve and I see things in the chat, by the way, I can't track that. So if there's something that needs my attention, please yell. But if you're talking among yourselves, that's great, that's fine. So you can solve the full pendulum equations, but only if gravity is fixed. And those ways are actually quite hard. They require elliptic functions, and you have to come up with a Mathieu equation. And something really interesting happens if gravity changes with time. Okay, so if you put your pendulum in an elevator and your elevator starts going up and down like this, of course they don't do that, but if you happen like that, that would mean that G is no longer G, it's G times sine of something or other. It's wiggling with a sinusoidal pattern, for example. We will actually play with the pendulum under this kind of forcing function in problem set 4. That makes things change, okay? So, and let me explain why that is. It's kind of sneaky. Okay. Did anybody find the focus button on this thing? If you did, please yell.
The dark gray button, we think.
Gray button. Okay. Got it. Thank you. All right. Now, let's see if we'll see if it does that next time. Thank you very much. Okay, so the original equations look like this. And oops, my G's are really bad. But now let's say we make this thing into capital G times sine of, I don't know, gamma t, something like that. We've put the pendulum in an elevator. And so gravity is being modulated up and down. Well, this does something interesting. It means that now, in order to know what the pendulum is going to do next, you need to not just know what the angle is and what the angular velocity is. You need to know what time is, because you need to know whether the pendulum is going up or it's going down. So now there are really kind of 3 state variables. I'll put some quotes there. Because you need to know theta, you need to know omega, and you need to know t in order to predict where the thing's going. So in this situation, this is, as I said, it's kind of sneaky. This is effectively (3D). So it can be chaotic, and indeed, for some values of that and some values of that, it is chaotic, and you will fight with those in problem set 4 because it's really kind of fun turning the knob on the drive frequency and seeing what happens. There is a mathematical way to think about this. By the way, non-autonomous systems. What is a non-autonomous system? A non-autonomous system is a system that has a variable on the right-hand side here's a variable. This is a constant, that's a constant, that's a constant, and so on and so forth. But this thing is a variable. If it has a variable on the right-hand side that's not over here, that's called non-autonomous. Okay, so if there's a t over here, that's no t over here, this is a non-autonomous system. There is a trick that you can use. You can kind of fake it. you can add another equation. You can say, okay, well, Liz just said if there's a variable over here, it's not over here, it's called a non-autonomous system. Well, maybe I can make it autonomous by making t into a state variable. And you make t into a state variable by sticking this equation to the system. And you have to get the physics right. So dt is always going to be 1, we hope, unless we're, relativistic. This also brings out the fact that this effectively changes the dimension of the system. And it also, hopefully, if going back to my picture of the box of mathematics that takes the state and tells you what's going to happen next, you need the theta, you need the omega, and you need the t in order to figure out what theta and omega and t are going to be next. Okay. All right. So how are we doing? We've got good 13 minutes left. Okay, did that. What have I got? Got the wrong. There we go. Okay. I did want to talk a little bit about this business of, sorry. There we go. This hand waving point I made before about the fact that nonlinearity and chaos are ubiquitous. And actually, let me draw this. That's better. All right, do this in the back of that. I'm wanting to draw this because I'll show you. So here is the set. This is an overwrought Venn diagram, but here is all the set of dynamical systems in the universe. That's what's in this Venn diagram. Here is the set of nonlinear. This is dynamical. This is nonlinear. Okay, and here is the set of chaotic systems. And why did I want to redraw it? I'll tell you in a second. This is the set of, here's all the chaotic systems in the universe. This in here is the stuff that the textbooks teach you about. Okay, this is the set of stuff that you learn about in linear algebra. Okay, this very thin band of stuff occupies 95% of the textbook. And then in here is the stuff that's in the very last chapter of the textbook, because it's very, very hard, but you can get some practice, some traction on it. Okay, so these are all the nonlinear systems that are not chaotic. So these things here are nonlinear, but they're solvable. And these things tend to have people's names attached to them because, it took somebody some serious work to figure out that you could solve, for example, I don't know, the Mathieu equation. But this is where the real world lies. And this picture has inspired all sorts of comments. There's a very famous nonlinear dynamicist who says that the study of nonlinear systems is like the study of non-elephant animals. Okay, so I hope the point's taken. And I hope the point's taken as to why you might actually want to be in this class learning about this stuff. And I redrew this, by the way, because if you look at my PowerPoint here, looks like there's a lot of stuff in here, but it's only that way because I had to have room to put the word in. Really, this is it's an onion. It's like an onion. There's a very, very thin skin of linear dynamical systems in the universe because the universe is almost all nonlinear. And of the nonlinear systems, there's only a very few that can be solved in closed form. And that's what the standard textbooks talk about. Most of an engineering education, at least, is that outer orange band, and then a bit at the end of the textbook on the green band. So I'm going to dive into a bit of storytelling for the rest of the class. Did we figure out whether that thing worked, the lock? Let me see if it works. That's better. Thank you very much, whoever looked that up. There we go. All right. So history. and storytelling. I'm cherry picking here. There's a lot more interesting things going on in the gaps here, but these are some of the kind of canonical, I won't use the word seminal because that has the other implication, canonical examples of nonlinear dynamics. I like to think that it goes back to Huygens, who was interested in building clocks. And he noticed that the clocks, they built clocks out of pendulums. That was the bob for the clock was a pendulum. That's how they kept time. And he noticed that if he put a whole bunch of clocks on the wall, on a single wall, that they would eventually synchronize. So what was happening there was there was the pendulum clock, the bob was actually moving the wall just a tiny bit, and that was coupling to the next clock and the next clock. And so they all ended up synchronized. So driven nonlinear oscillators can synchronize. Poincaré, Henri Poincaré, came along in the late 1800s, and I view him as the grandfather of the field. He was actually quite an amazing guy. Let me find this quote. So Poincaré came up with relativity before Einstein. He also came up with the notion of time as a fourth dimension and the notional gravitational waves and E equals mc squared, although he didn't quite write it down that way. So that was Poincaré. But from the standpoint of our course, Poincaré was interested in, among other things, the long-term stability of the solar system, which was the topic of a competition organized by the King of Sweden at the time, with a fairly substantial prize offered for anybody who could establish whether or not the solar system was stable. And Poincaré solved that. He did a lot of inventing of the field of topology in order to do that. So he was just an amazing guy, and he was the grandfather of our field. Then along came Lorentz in the early 60s. And this picture right here is a picture of the solution, a numerical solution to Lorentz's equations. Lorentz was a meteorologist. He was interested in how the fluid dynamics and the heat transfer of weather, of air, of an air mass. And his equations, and we'll play with them a lot, were constructed to model what happens if you have a chunk of fluid and you heat it from below. And you've all cooked, so you know what happens. Your oatmeal kind of forms convection rolls. And so that's the state variables of Lorentz's system are kind of like that. And these are kind of like convection rolls. And again, we'll come back to it. So what Lorentz did was solve those equations. So he came up with those equations and he solved them actually at the time on an analog computer. Notice 1960s, no widespread digital computer going on here. So instead he used an analog computer, which is basically you can build a differential equation out of resistors, capacitors, and operational amplifiers. And we'll talk a bit more about that. So he did that and he generated trajectories that look like this. And he was the one who figured out that if he started the system in a slightly different state, you would get the same overall pattern, the same overall long-term asymptotic pattern, which is called an attractor. But depending on where you started, the trajectory, the path might trace out that pattern in a different order. So he discovered sensitive dependence on initial conditions in the context of a fixed geometric attractor. And as we'll talk about later, this had been seen before, but it controverted the prevailing dogma in his field. So part of what's amazing about Lorentz is he didn't, like everyone before him, throw it out because it was not possible because of the dogma. He actually embraced it and went with it, ran with it. So he actually, he did not give the field its name because he chose a rather boring name for this behavior. He called it deterministic non-periodic flow, which does not trip off the tongue. Then Jim York came along, maybe 10 or 15 years later, and he rediscovered this in a limited context. And he wrote a paper, he and his student Lee wrote a paper with the title period 3 implies chaos. So Jim was the first person to use the word chaos. He named the field. He did not discover the behavior. Then there was all sorts of stuff that happened. There was a group at the University of California at Santa Cruz that were interested in writing down the differential equations for a roulette wheel and using that to make money. And there's a great book about that. I have a link to it on my webpage. Many of those people went on to build the field, and most of them are still in it. Then, things really blow up, and along comes Jack Wisdom, and he gets interested in the problem that dated back to Poincaré and the King of Sweden as to whether or not the solar system was stable. And so he and my advisor, Jerry Sussman, built a computer that was fast enough at the time to explore this, which is now in the Smithsonian. And they showed that the orbit of Pluto is chaotic. So had the money still been around from King of Sweden, Jack and Jerry would have won it. And then your textbook author, Steve Strogatz, has done all sorts of cool stuff, including analysis of firefly synchronization, and also you may remember this, actually some of you may not. There was a bridge called the Millennium Bridge built in London, and it had a really unfortunate instability, and it started wiggling side to side when anybody walked on it, and Steve did an analysis of that. So there's many, many more of these. I've put the kind of canonical paper from each of these up in the problem set. And by the way, each problem set has a section at the beginning. I should show you that, and we'll quit. There we go. Don't want that. I want back. Sorry, my Zoom window is on top of this. Let's do back. Okay, so here's a problem set that's nominally issued today, and it's nominally due 1 week from today via the course page. Here's some reading. Some of it's in Strogatz. If you don't take advantage of the stuff on Canvas, you can just wait and read it later. There's required readings and optional readings in different font. Here's some information about the videos. Here's some bibliography, and here are the problems. And we will get into the material to do these problems later on, but what you should do, please, is take a look at the syllabus, because I will abide by it. And go to that MOOC. Here's the link, and register for that course and dig around a little bit. And then what we'll do on Thursday is finish my hand-waving storytelling about the history, and we will dig into the material to do this problem. So with that, I think I've managed to end on time. Thank you all for being here. Thank you for having your cameras on. That actually helps in the social psychology of the classroom in a way that mimics what happens in a real classroom, and that makes a big difference. And again, I'll see you all in person in the 2 weeks minus an hour and 15 minutes. And I will see you all again online in 2 days. Thank you very much. And I always play music when I'm waiting, when I fire up the Zoom. If you have requests, email me. All right, take care.
Thank you.